Today we're diving into the world of cross-validation techniques, a cornerstone in the field of data mining. Cross-validation is a powerful method used to assess how well our predictive models perform on unseen data. By the end of this video, you'll understand why cross-validation is so essential, especially when working with large datasets and complex algorithms. We'll start by exploring the basic idea behind cross-validation, then move on to different techniques, their advantages, and practical tips for implementation. Let's begin our journey into making your models more reliable and robust. Data mining, building a model, is just the first step. The real challenge lies in ensuring that your model performs well on new, unseen data. This is where cross-validation comes in. It helps us estimate the generalization ability of our models, reducing the risk of overfitting. Overfitting happens when a model learns the training data too well, including its noise and outliers, and fails to perform on new data. Cross-validation provides a systematic way to evaluate and compare models, making it a crucial step in any data mining workflow. Its core, cross-validation, involves splitting your dataset into multiple parts or folds. You train your model on some of these folds and test it on the remaining ones. By rotating which folds are used for training and testing, you get a more accurate picture of how your model will perform in real-world scenarios. This process helps ensure that every data point gets a chance to be in both the training and testing sets, leading to a fair and thorough evaluation. One of the simplest cross-validation techniques is the holdout method. Here you split your data into two sets, one for training and one for testing. Typically about 70% of the data is used for training and the remaining 30% is reserved for testing. While this method is straightforward and quick, it can be sensitive to how the data is split. If the split isn't representative, your model's performance estimate might not be reliable. Despite its simplicity, the holdout method is a good starting point for beginners. K-fold cross-validation is one of the most popular techniques. In this method, the dataset is divided into k equal size folds. The model is trained on k1 folds and tested on the remaining fold. This process is repeated k times, with each fold serving as the test set once. The results are then averaged to provide a robust estimate of model performance. K-fold cross-validation is widely used because it makes efficient use of data and provides a balanced evaluation. Selecting the right value for k in k-fold cross-validation is important. Common choices are 5 or 10, but the optimal number depends on your dataset size and computational resources. A smaller k means larger test sets and fewer training samples, while a larger k increases computation time but provides a more thorough evaluation. Balancing these factors is key to getting reliable results without unnecessary overhead. Stratified k-fold cross-validation is a variation designed for classification problems, especially when classes are imbalanced. It ensures that each fold has a similar distribution of class labels as the original dataset. This approach prevents scenarios where some folds might lack certain classes, leading to more reliable and consistent performance estimates. Stratified k-fold is particularly useful when working with rare events or minority classes. Leave-one-out cross-validation, or LOOCV, is an extreme case of k-fold where k equals the number of data points. Each time the model is trained on all data except one point, which is used for testing. This process repeats for every data point. LOOCV provides an almost unbiased estimate of model performance, but can be very computationally expensive, especially with large datasets. It's best suited for small datasets where every data point is valuable. Leave-p-out cross-validation is a generalization of LOOCV. Instead of leaving out one data point, you leave out p points for testing and train on the rest. This method is rarely used in practice because the number of possible combinations grows rapidly as p increases, making it computationally intensive. However, it provides a very thorough evaluation and is sometimes used in research settings with small datasets. Repeated k-fold cross-validation involves performing k-fold cross-validation multiple times with different random splits. This approach helps reduce the variability in performance estimates caused by a single random split. By averaging the results across repetitions, you get a more stable and reliable measure of your model's generalization ability. It's especially useful when your dataset is small or when you want to minimize the impact of randomness. Monte Carlo cross-validation, also known as repeated random subsampling, randomly split the dataset into training and testing sets multiple times. Each time the model is trained and evaluated and the results are averaged. This method is flexible and allows you to control the proportion of data used for training and testing. However, some data points may never be used for testing, and others may be tested multiple times, which can introduce bias. When working with time series data, standard cross-validation methods may not be appropriate due to the temporal order of observations. Time series cross-validation, such as rolling or expanding window methods, respects the sequence of data. The model is trained on past data and tested on future data, mimicking real-world forecasting scenarios. This approach helps prevent data leakage and ensures that your model's performance estimate is realistic. Nested cross-validation is used when you need to tune hyperparameters and evaluate model performance simultaneously. It involves two loops, an inner loop for hyperparameter tuning and an outer loop for performance estimation. This method helps prevent overfitting during model selection and provides an unbiased estimate of how your model will perform on new data. Nested cross-validation is especially important in research and competition. Cross-validation isn't just for classification problems, it works equally well for regression tasks. The same techniques like k-fold and LOOCV can be applied to evaluate how well your regression model predicts continuous outcomes. The key is to use appropriate performance metrics such as mean squared error or mean absolute error to assess your model's accuracy during cross-validation. For classification problems, cross-validation helps you assess how well your model distinguishes between different classes. Techniques like stratified k-fold ensure that each fold has a balanced class distribution, which is crucial for fair evaluation. Performance metrics such as accuracy, precision, recall, and F1 score are commonly used to summarize results across folds. Choosing the right performance metric is essential in cross-validation. For regression, metrics like mean squared error and R-squared are popular. For classification, accuracy, precision, recall, and F1 score are widely used. The choice of metric should align with your project goals and the nature of your data. Consistently applying the same metric across folds ensures meaningful comparisons. Cross-validation helps you navigate the bias-variance trade-off in model evaluation. High bias means your model is too simple and underfits the data, while high variance means it's too complex and overfits. By using cross-validation, you can identify the sweet spot where your model generalizes well to new data, balancing both bias and variance for optimal performance. One of the main benefits of cross-validation is its ability to reduce overfitting. By repeatedly testing your model on different subsets of data, you ensure that it doesn't just memorize the training set. Instead, it learns patterns that generalize to new data. This process leads to more robust models that perform well in real-world applications. Cross-validation is a valuable tool for model selection. By comparing the performance of different algorithms or parameter settings across multiple folds, you can identify which model is likely to perform best on new data. This systematic approach takes the guesswork out of model selection and helps you make data-driven decisions. Hyperparameter tuning is the process of finding the best settings for your model. Cross-validation plays a key role here by providing a reliable way to evaluate each combination of hyperparameters. Techniques like grid search or random search combined with cross-validation help you optimize your model without overfitting to the training data. In implementing cross-validation, there are a few practical tips to keep in mind. Always shuffle your data before splitting unless you're working with time series. Use stratified folds for classification tasks to maintain class balance. And remember, cross-validation can be computationally intensive, so plan accordingly if you have a large dataset or complex models. Despite its benefits, cross-validation has some common pitfalls. Data leakage, where information from the test set leaks into the training process, can lead to overly optimistic results. Not shuffling data properly or using inappropriate folds can also skew your evaluation. Being aware of these issues helps you avoid mistakes and ensures your results are trustworthy. Real-world projects, cross-validation is often implemented using libraries like scikit-learn in Python or caret in R. These tools provide built-in functions for various cross-validation techniques, making it easy to integrate into your workflow. By leveraging these libraries, you can focus on building and improving your models rather than coding cross-validation from scratch. In working with big data, cross-validation can become computationally expensive. Techniques like parallel processing or using smaller representative samples can help manage the workload. It's important to balance thorough evaluation with practical constraints, ensuring that your cross-validation process remains feasible and informative. Balanced datasets, where some classes are much less frequent than others, pose unique challenges for cross-validation. Stratified k-fold is especially useful here, as it ensures each fold has a similar class distribution. Additionally, using appropriate performance metrics like the area under the ROC curve can provide a more accurate assessment of model performance on imbalanced data. Feature selection is the process of choosing the most relevant variables for your model. Cross-validation can help you evaluate different feature subsets, ensuring that your final model includes only the features that truly improve performance. This leads to simpler, faster, and more interpretable models. Ensemble methods like bagging and boosting combine multiple models to improve performance. Cross-validation is often used to evaluate and tune these ensembles, ensuring that the combined model generalizes well. By systematically testing different configurations, you can build powerful ensembles that outperform individual models. Deep learning models often require large datasets and significant computational resources. While traditional cross-validation can be challenging due to training time, techniques like holdout validation or using a validation set are commonly used. In some cases, k-fold cross-validation is applied with smaller models or datasets to ensure robust evaluation. Cross-validation isn't limited to supervised learning. In unsupervised learning, such as clustering, techniques like internal validation indices or stability analysis can be used to assess model quality. While the process differs from supervised tasks, the goal remains the same: ensuring your model generalizes well to new data. Data preprocessing steps, such as scaling or encoding, should be performed within each fold of cross-validation to prevent data leakage. Applying preprocessing to the entire dataset before splitting can lead to overly optimistic performance estimates. Always fit your preprocessing steps on the training data and apply them to the test data within each fold. Cross-validation not only helps you build accurate models but also supports interpretability. By evaluating different models and feature sets, you can identify which variables are most important and how they influence predictions. This transparency is valuable for stakeholders and helps build trust in your models. Automated machine learning (AutoML) platforms often use cross-validation to evaluate and select the best models automatically. By integrating cross-validation into the AutoML pipeline, these tools can efficiently search for optimal algorithms and hyperparameters, saving time and improving results for users. Before deploying a model into production, cross-validation provides confidence that it will perform well on new data. By thoroughly evaluating your model, you reduce the risk of unexpected failures and ensure a smoother transition from development to deployment. This step is critical for building reliable data-driven applications. Even after deployment, it's important to monitor your model's performance over time. Cross-validation can be used periodically to reevaluate the model as new data becomes available. This ongoing process helps detect performance drift and ensures your model continues to deliver accurate predictions. Reproducibility is a key principle in data science. By using cross-validation and documenting your process, you ensure that others can replicate your results. This transparency is essential for collaboration, peer review, and building trust in your findings. In academic research, cross-validation is a standard method for evaluating new algorithms and models. By providing a fair and unbiased assessment, it allows researchers to compare results across studies and advance the field of data mining. Proper use of cross-validation strengthens the credibility of research findings. Data science competitions like those on Kaggle often rely on cross-validation for model evaluation. Competitors use cross-validation to fine-tune their models and maximize performance on unseen test data. Mastering cross-validation techniques can give you a competitive edge and improve your results in these challenges. Ethical AI requires models that are fair, unbiased, and reliable. Cross-validation helps identify and mitigate biases by providing a comprehensive evaluation across different data subsets. By ensuring your models are thoroughly tested, you contribute to building ethical and trustworthy AI systems. Robust models perform well under a variety of conditions. Cross-validation tests your model on different subsets of data, exposing it to a range of scenarios. This process helps you build models that are resilient to changes in data and maintain high performance in real-world applications. In business, reliable models drive better decisions and outcomes. Cross-validation ensures that your predictive models are accurate and trustworthy, reducing the risk of costly mistakes. By investing time in thorough evaluation, you maximize the value your models bring to your organization. Communicating your cross-validation process and results is important for transparency. Clear documentation and visualizations help stakeholders understand how your models were evaluated and why they can be trusted. Effective communication builds confidence in your data-driven solutions. The field of data mining is constantly evolving, and so are cross-validation techniques. Staying up to date with the latest methods and best practices ensures that your models remain competitive and effective. Continuous learning and experimentation are key to mastering cross-validation. Let's recap what we've covered. Cross-validation is a vital tool in data mining for evaluating model performance, selecting features, tuning hyperparameters, and ensuring robust, reliable results. By understanding and applying different cross-validation techniques, you can build models that generalize well and deliver real value. Cross-validation is more than just a technical step. It's a mindset that prioritizes thorough evaluation and continuous improvement. Whether you're a beginner or an experienced data scientist, mastering cross-validation will elevate your work and help you build models you can trust. Keep exploring, keep learning, and let cross-validation guide your journey in data mining. Thank you for joining this deep dive into cross-validation techniques in data mining. Now that you have a solid understanding of the concepts and practical tips, you're ready to apply these methods to your own projects. Remember, the key to success is consistent evaluation and a willingness to learn from your results. Good luck on your data mining journey.